Okay, so this is a text by Calculus Volume 1 by OpenStax. This is an open source textbook that we're using for in class. And let us go through how the book presents the fundamental theorem of calculus. Okay. So the book says that the fundamental theorem of calculus is an extremely powerful theorem that establishes the relationship between differentiation and integration. And it gives us a way to evaluate the definite integrals without using Riemann thumbs or calculating areas. Just recall what you've read in the previous chapters or sections on the definite integrals using Riemann thumbs. If you recall, the definite integral using Riemann thumbs was able to get the area of a region bounded by a curve. Okay, the theorem is comprised of two parts. The first of which is the fundamental theorem of calculus part 1, which is what we'll be reading today. And this part establishes the relationship between differentiation and integration. Okay, so specifically, fundamental theorem of calculus part 1 or theorem 5.4 states that if you have a function small f of x continuous over an open interval ab, and you have another function big F of x defined by equation 5.16, or if you have big F of x defined as the definite integral of f of t dt from a to x, then f of x, then the derivative of big F of x is equal to small f of x. This is the derivative of big F of x over AB. Okay. Okay. Again, let's do this statement by statement. You have two conditions. Okay. The fundamental theorem of calculus gives us a theorem that defines the derivative of a certain function. Okay, f prime of x, big F prime of x. It says that it is equal to small f of x. Now, what are the conditions that these functions need to satisfy or need to meet for this statement to be true? First, so we have two statements. First, we have this statement. This has to be true, meaning we need to have a continuous function that is small f of x over an over a closed interval AB. And then second is we need this statement to be true. Okay? We need another function denoted by f, big F of x, and that function must be equal to the definite integral of small f of x from a to x. Now, if we have these two functions, if these two functions are correct, or if these two functions hold, then this should be true. Okay, now for us to understand this theorem, we need to go over the proof. We need to study the proof. But before we do that, let us first read what the book tells us. Okay, so the book says that before we delve into the proof of a couple of subtleties are worth mentioning here. So first, a comment on notation. Note that we have defined a function big F as the definite integral of another function small f from point A to point X. Okay. Okay, that if there is a relationship between big F and small f. So big F is the definite integral of small f from point A to point X. At first glance, this is confusing because we have said several times that the definite integral is a number. Why is the definite integral a number again? If you recall the previous sections on definite integrals, you'll know that the definite integral is the area, or denote the area of a region. Remember, the definite integral denotes the area of a region bounded by the graph of f of x, or y equals f of x, the line x equals a, the line x equals b, and the x-axis, or the line y equals 0. This is able to produce a region, a closed region, and let's name it R. The area of this region is given by, so the area of R is given by the definite integral from a to b of f of x dx. That's why it says that the definite integral. That's why the definite integral has to be positive. And here it looks like it's a function. It looks like it's a function because one of the bounds is a variable x. Okay, so the key here is to notice that for any particular value of x, the definite integral is a number. Meaning if you substitute a specific value of x, you will get a number as a value for your definite integral. So the function big F of x returns a number, which is the value of the definite integral for each value of x. Now, second, that it's worth commenting is the implications of this theorem. So there is a reason why it is called the fundamental theorem of calculus. Okay, not only does this establish the relationship between integration and differentiation, but it also guarantees that any integrable function has an antiderivative. Okay, so specifically, it guarantees that any continuous function has an antiderivative. Okay, any continuous function has an antiderivative. Okay, so now let's study the proof. Okay, and then we will try to fill in the gaps. Okay, applying the definition of the derivative. Okay, what is the definition of the derivative? This is the definition of the derivative. Remember? The derivative of a function, let's say big F, is equal to the limit as h approaches 0 of the difference between big F of x plus h and big F of x over h. Okay. Now, it says that this statement follows, the second statement follows from the first statement. How is this possible? Let us recall the premises to your theorem. Okay. So I'll write it here. What are the premises? What are the given? What did we assume to be true? F is continuous. Okay, f of x. See? F of x is continuous on the closed interval AB, and then another is big F of x is defined to be the integral from a to x of f of t dt. Okay. So if big F of x is the integral of f of t dt from a to x, then it follows that f of x plus h. Okay, the original argument of the function is x. Now the argument is x plus h, meaning we will replace x with x plus h is equal to the integral from a to x plus h of f of t dt. So that's why we have this. Okay. So basically, the first thing that we did, we just factor this out of the fraction. That's why it's here. And then, based from the premises of the theorem, f of x plus h is equal to this. So that's, we just replaced that here. We substituted that here. And f of x, well, f of x, based on the definition, is the integral of f of t dt from a to x. So that's what we have. Okay. Now, what happened here? From the second line, we get to the first line. If you recall again, another recall, if you have the integral from a to b of, let's say, f of x dx, this is just equal to the integral, the negative of the integral from b to a of f of x dx. So that is what happened here. Okay, so observe what happened. The bounds on the second term interchange. Initially, it was from a to x. Now it is from x to a. Okay, so this has to be negative. But since it's preceded by a minus sign, then it becomes positive. So this is what happens. Before the third line, we have this. Okay, right. So there has to be something. Okay, I'll use a different color. There has to be something here. There has to be something here before the third line. And what should we write there? Okay, I'll use a different color, maybe pink. Okay, so what should I write here? This should be, okay, for a while, this should be the limit. Okay. Let me use a thicker pen. Okay, so this should be the limit as h approaches 0 of what? 1 over h times, I'll just copy the first term, a, the definite integral from a to x plus h of small f of t dt minus negative of the definite integral of f of t dt. Since it's negative, then meaning I'll have to twist, I'll have to change the bounds. Instead of having from a to x, then I would have from x to a. Okay. If we simplify this, negative and negative becomes positive. So that's why we have the third line. Okay, now, so what happened here? How did this fuse into one? Okay, in here, okay, what happened here? Okay, the original line 1, 2, 3, 4. Okay, recall we have the integral from a from the definite integral from a to x plus h of f of t dt plus the definite integral from x to a of f of t dt. Okay. If we rearrange this, since addition is commutative, I can rewrite this as the integral from x to a of f of okay. Now, if we simplify this, what do we get? Look at the bounds. From x to a, then from a to x plus h. So, if we just look at the interval, this is on the interval x to a. And then this is on the interval a to x plus h. So, basically, we have the interval from x to x plus h. And since we have the same argument, or integrand, we have f of t. So we can say that this statement is just equal to the definite integral of f of t dt from x to h. That's why we have this. Okay. Now, so looking carefully at this expression, we see that 1 over h times the definite integral of f of t dt from x to h is just the average value of the function f. What does it say? It's just the average value of the function f over the interval, the closed interval x to x plus h. So therefore, by the mean value theorem for integrals, there is some number c such that, what does it say? There is some number c such that this is true. Okay, what does the mean value theorem say? So the mean value theorem says that if you have a function continuous, let's say f of x continuous on AB, then this is for the derivative. Then we can find a c in AB such that f prime of c is equal to f of b minus f of a over b minus a. Now, the mean value theorem for integrals is a direct consequence of the mean value theorem for derivatives. So I'll just write it here. The mean value theorem for integrals says that the integral of f of x dx from a to b is equal to f of c times b minus a. Okay, so let's look at the notation used in the book. Okay, so the lower bound is x for this case. The lower bound is x and the upper bound is x plus h. So this is our b. So b minus a would be, okay, so b minus a would be the lower bound minus the upper bound, which is x plus h minus x or h. So for this notation, b minus a is equal to x. This tells us that we can find a c in the closed interval x to x plus h such that the integral of f of t dt from x to x plus h is equal to f of c times h. Or f of c, you transpose h to the other side, you'll have 1 over h integral x plus h f of t dt. Okay, so let's continue. So we ended with f prime of x equals the limit as h approaches 0 of 1 over h times the definite integral of f of t dt, t from x to x plus h. And then we know from the mean value theorem of calculus that this is what? What is this equal to? This is just f of c. So this is equal to the limit as h approaches 0 of f of c. Now, to evaluate this limit, note that, what do we see? C is between x and x plus h. Or we can write this equivalently as x is less than or equal to c and c is less than x plus h. And since we are letting h approach 0, what would happen to c? Okay, if h approaches 0, this is the upper bound of c. So if h approaches 0, x plus h would approach x. So we say that if h approaches 0, then c would approach x. Therefore, we say that the limit of f of c as h approaches 0 is equal to f of x. And our proof is complete. So therefore, big F prime of x is indeed equal to small f of x.